So we're going to proceed today's wet lab that deal with the radiation-induced chromosome damage and rejoin. And we'll go through the same sequence of outlines as we did before. Start with a little bit background of chromosome aberrations and their relationship to dose response. And then after that, we will give you a sort of detailed outline what kind of equipment, supplies, and procedures that you need to know in order to do a good chromosome preparation so that you can use the chromosome spreading for this type of study. And we add a line of troubleshooting tips for today's lecture because unlike some of the wet labs that we had before, this particular method of chromosome spreading is relatively simple, but on the hand, that does involve a little bit art than science, so that in order to get a good final product, you have to know some of these things. That's why we include here. And finally, we'll tell you what kind of thing you're going to do the next hour. A little bit about background, which we're going to reacquaint you with different type of chromosome aberrations so that during the next hour, when you see the actual samples, you will be able to identify what type of chromosome damage you are looking at it. And also, we will do this dose response curve again so that you know and what dose, what radiation condition that will change the chromosome aberrations. So let's start with this picture, and this is a way that you can show how radiation-induced chromosome damage. In this case, you have two radiation rays hit through a nucleus of a cell, which you cut through, say, 3 chromosomes, and this supposedly happen at the G1 phase of the cell cycle because most of the chromosome aberration done will use the lymphocyte. They are mostly in the G1 phase of the cell cycle. In this case, you cut through the 3 chromosomes in different part of their morphological area. And after the damage are done, there are at least 3 possibilities that the cells or chromosomes trying to repair themselves. They could rejoin back to their original chromosome on each individual pieces, and that will be like nothing happens. They get complete repair, then they go through the cell division and they go through the normal cell cycle, and the cell lives. The second case that you could have a different kind of joint, that if this piece goes there, this piece goes there, that piece goes here, that piece goes there, then you have this kind of translocation or reciprocal translocation. In that case, and you involve some of the gene rearrangement because the gene on this piece of chromosome will be connected to that piece of chromosome. But on the hand, if this kind of gene rearrangement doesn't really affect function very much, structurally or morphologically, the chromosome will still look very intact because you have both arms connect to the centromere, then the cell will go on, go through the mitosis and the divide, and the cell probably will survive. Or you have a very extreme case, in this case, that instead of adjacent exchange, you have the extreme exchange where this piece of long chromosome will exchange to this piece, and also this piece of chromosome will exchange to that piece. Then you wind up with this very long piece of chromosome which contains the centromeres from all 3 of them. So you have 3 centromeres and also 2 pieces of chromosomes without centromeres at all. In this case, then when the cells move through that part of cell cycle, go to the mitosis, you have a problem because the centromere will try to move into the opposite end at the end of a metaphase or the anaphase. In that case, they will try to pull this thing apart, but they couldn't because they all connect together. So eventually, this type of exchange will result in a cell death. So if you look everything like that, and then also put the cell cycle into your consideration, because we said that the thing could happen at the G1, then the exchange, the other things would take place in S and G2M. But if you look at the cell cycle, some of the important areas that if the radiation is done at G1, the radiation will only hit on a single chromatid. But if the radiation done on the G2 or S phase, then you have two pieces of chromatid. Okay. Then also the period that it's very important for you to look this chromosome in the mitosis, especially in the metaphase. So keep these things, these relative positions in mind. Then if you look at the chromosome aberration again, you can divide the chromosome aberration into two types. It's called chromosome aberrations or chromatid aberrations. Chromosome aberration happened when the damage was done at the G1 phase of the cell cycle. At that time, you only have one chromatid, and during the metaphase, both chromatids will show the same type of damage. Or you have chromatid aberrations. That's when the radiation was given at SOG2M part of cell cycle. Then you may only see one of the chromatid involved in aberration or damage. Now, let's go through some of the possibilities of the chromosome aberrations or changes. In this case, the first case, you will involve two pieces of chromosomes, and the radiation cuts through both of them, so you get a break on each one of the chromosomes. And then they'll try to rearrange among themselves, or in this case, that piece of chromosome will stick to that piece of chromosome. You get this kind of, they call the illegitimate union, and then wind up a piece of chromosome with two centromeres. So you have a dicentric chromosome plus an acentric fragment, the fragment without any type of centromere. So this is the one type which involves two pieces of chromosomes. Or you could have a situation that happen on the same piece of chromosome, but during the G2 part of cell cycle, where you have two pieces of chromatid. So this is one chromosome, but two chromatid. Radiation cuts through this chromosome, so you have called isochromatid deletion. In this case, both ends are cut off, and then this remaining part of the chromosome, the two chromatid will join together, called the sister union, and result into this kind of structure. When this piece of chromosome try to separate, and it will produce another centromere, but the centromere cannot really pull apart during the anaphase, then you wind up have two centromeres and look like a bridge. And since this only can be observed at the anaphase, so this is called anaphase bridge, a symmetrical dicentric chromatid. Don't worry about this terminology, just that you know how it happened. And the remaining part of the chromatid from both strands will form a eccentric fragmentation. Same thing could happen on the single chromatid. That's at the G1 phase of cell cycle. The example we showed before happened at the G2M, where you have two chromatids. Now you have one chromatid, or you call it chromosome. And the break happened on both sides of the arm, on both sides of the centromere, and then they'll form together, join together, and form a ring. The remaining two pieces stick together as a piece of fragment. This ring goes through the S and G2M part of cell cycle, will duplicate the ring, and you have two centromeres, and they actually can stuck together and form these overlapping rings and plus eccentric fragment. So let's take a look at some of the real chromosome spreading that shows that exactly the same structure would happen. In this case, it will be dicentric and eccentric. And that will be the ring structure. Okay. Now, can you remember how did the ring structure happen at the G1 or G2 phase of cell cycle? This is a good question for exam.
G1.
Yes. And this is that anaphase bridge formation, because you have the chromosomes pulled apart to two sides of the cells. But this piece of chromosome, because it has two centromeres, one pulls this part, that pulls that part, but cannot go along, so it's stuck in the middle. It's called anaphase bridge formation. And if you look this again, the several dicentric structure here. You have dicentric, there you have dicentric, and there you can see that there's a tricentric, three centromeres. And these are all the examples of different type of chromosome exchanges. Now, we have described this type of ring formation, and so you have a ring with a centromere. But There's other cases you could get a ring without centromere. That was because this happened when both ends of the arm is broken, so you can form a ring with a centromere. But if the radiation cuts through only one side of the arm, and so you produce this interstitial deletion, and that piece of a chromosome form a ring by itself, and you get a ring without a centromere, but the remaining chromosome will be joined together again, and they look like a sort of normal chromosome. If you don't count on the function of the chromosome, they can go through the cell division, but these two small rings cannot divide and were eventually lost. And this type of ring structure is commonly observed as a micronuclei, which we're going to discuss the next time when we do the lab rotations. And so this is one of the ways, one of the most common ways to form a micronuclei. And that's why this kind of ring is called the eccentric ring. Again, we can look some of the actual example. You have the ring here with the centromere, and there you have a normal looking chromosome pair with a centromere, but indeed part of the chromosome is lost to form these two rings, or you can call it as the micronuclei. Now, so far everything we look are categorized as chromosome aberrations. Everything you see, all of the chromosome either deleted or exchanged, but form a very distinct structure. But in this case, we can also see the chromatid deletion. This is when the radiation was given at S or G2 part of cell cycle, where only one part of the chromatid, there's two of them, one part will get deletion, so you get the chromatid deletion. Otherwise, you get the chromosome deletion if both chromatids are involved. And the remaining part of the deletion, if this is sort of on both sides of a chromatid, you get this isochromatid deletion. And this is also one of the ways that you can make the other kind of a formation, that is the bridge formation. Now, in addition to those very defined structures and process, there's many types of exchange that just no name for it. It's very complicated. For instance, this one you can call it asymmetrical quadrant radio, or this is very complicated, just involve many pieces of chromosomes sort of exchange together to a very complicated structure that you cannot put them apart in any fashion. Now, among all these different kind of exchanges, some of the exchanges are not very lethal. For instance, if exchanges involve the translocation, or especially the reciprocal translocation, that is one part of chromosome is exchanged with other part of chromosome, and these two chromosomes are very similar in size. So if you look at the growth morphology, you really couldn't tell whether this exchange occurred between these two chromosomes. And plus the situation where these two pieces of chromosome contain either non-essential information, or the informations can be functioned independently of their chromosome location, then you're not going to get any defect for the entire cell function. So most of the time, this reciprocal translocation will allow the cell to survive, even function normally. In other cases, you get a small deletion out from one piece of a chromosome, and the other piece will join back again. So look morphologically, you really couldn't tell whether you're missing that piece or not. And again, if the information on this piece is non-essential, then the cells really don't need this type of piece, this piece of chromosome. The cell can survive subsequently. So overall, the chromosome rearrangement is the best biomarker for the radiation exposure. That's why it's a gold standard for biodosimetry for any kind of conditions, either for risk assessment or for health concern, simply because this type of measurement is very sensitive. You can get down to 0.1, 0.05 gray range. It's very reliable. That is, some of the information can be stored in the cells for a long period of time. For example, some of the circulating lymphocytes in human beings can retain this kind of information for up to 10 years, so that you don't need to have an immediate measurement of the samples. And for example, some of the atomic bomb survivors, if you take the lymphocyte from those survivors, you can still get a good estimation of what type of radiation or how much radiation those survivors have received many, many years ago, even though the reliability getting less and less because it's been almost 50-some years since those people received the initial dose. There's a large database available there so that if you don't have sufficient information, you can compare back to that database to extrapolate your data back to those large databases to get estimating of how much radiation dose an individual has received. Now, in addition to the classical morphological observation of chromosome aberration, you can use one of the new techniques. This is not new anymore. This is at least like 20-some years old. The FISH technique, which will give you additional information than just the simple growth morphology. In this case, if you can paint the individual chromosome with different colors, for example, cells without radiation will show a uniform color distribution on each individual chromosome. After radiation, if you have an exchange among different pieces of chromosomes, you get a mosaic of colors, any mosaic indicating a chromosome exchange. So this not only will allow you to determine how much exchange, what exchange happened, and also will give you the estimation of the radiation dose, meaning the higher the radiation dose, the more the frequency of the exchange will happen. And also this is a great method of reviewing those reciprocal translocation where you really couldn't tell from a simple morphological observations. Or, for instance, in this case, you can have a marker for the centromere, so you don't have to worry about the details of chromosome. You just count those bright dots because each dot represents a centromere. This is an example of a tumor sample. You know, most of tumor cells have multiploidy or polyploidy. So first you can just count how many dots to know the ploidy of the cell. Secondly, you just count how the dots are distributed on each chromosome. Then that immediately will give you the information about dicentric, tricentric, whatever. So it's a very useful way of reviewing much more details and also speed up many of the chromosome aberration measurement. So once the arrangements are made or deletions are made, what happened to those lesions? Of course, there's another case which I didn't list here, that's number 0. If they repair properly the original chromosome, rejoin back to their original host, then nothing happens. But if, say, the small piece of chromosome breaks from the original host and lost at the mitosis, in this case we get a micronuclei, and in most of the cases this could be a lethal event if that piece of chromosome contains very useful information. And the second type is the exchange type of rearrangement, and that can be divided into 3 categories. That is, you could have a symmetrical rearrangement. In this case, the typical example would be that the reciprocal translocation. In this case, we call the balanced rearrangement. Most times, they will not involve any kind of lethality because the whole cell will contain the complete information or genomic structure of the cell. And the second type is asymmetrical. In this case, one chromosome may get more information than other chromosome. It depends on the amount of the rearrangement and also the critical information of that piece of information. The cell may or may not survive. And finally, you have these polycentric chromosomes, dicentric, tricentric, manycentric. And most of these chromosomes will eventually lead to the cell death or aneuploidy through this kind of a process. Now, finally, we want to review quickly through the dose response of chromosome aberrations. Since there's 2 types of chromosome aberration, deletion and rearrangement, so we will talk about them individually. First, about deletion. The relationship between radiation hit and amount of deletion is very simple. Most of the time, it's a 1 hit, 1 deletion. For instance, if the terminal deletion, if the hit or the breakage occurred at the end of the chromosome, 1 hit, 1 deletion. Or chromatid deletion is 1 hit. Interstitial deletion, you may need 2 hits. That is, you cut the middle of a chromosome off, and that part of a chromosome become lost, or there's no rearrangement loss. But majority of them will be one hit. With a one hit, one deletion relationship, the yield of the chromosome aberrations will be represented by this very simple linear equation. Y equals K plus alpha D. Y is the total yield, how many aberrations per 100 cells. K is a constant for the background chromosome aberrations. And alpha would be some kind of dose relationship, for instance, different type of radiation, X gamma ray versus neutron alpha particles. Then you have different constant here. So it's very easy to understand. Now, when you get into the rearrangement type of chromosome aberrations, you definitely need two hit, because you need two break point to make arrangement. And this two hit, not only two hit, also the two hit, they have to happen at a particular time and space. That is, you have to have the two broken pieces in approximate close condition in order to make a rearrangement. If the two pieces are far away, you're never going to make the rearrangement. What happens is you get deletion. If they cannot make a rearrangement, you get two deletions. Also the time. If the radiation is given at the very close to the mitosis time, then the cells really don't have enough time to make that rearrangement. Then you're going to get deletion. There's no rearrangement. So, but if you look for the dose-response relationship, since you need a two hit, so it's the square of the dose that dictate the yield of this type of chromosome aberrations. So the yield is K plus beta D to the square. So the total yield, the combination of the deletion and the rearrangement, will be represented by this equation, which is this curve. And that's just a single hit, that's just deletion. If you have the combination deletion and the rearrangement, it will be represented by this curve. And also, if you look at the dose versus aberrations, most of the aberration at the lower doses is represented by a single hit or deletion. But at a higher dose, once the dose getting higher, you have more of the rearrangement type of aberrations. And this can be explained very simply by plugging some numbers to this equation. And this is the equation, the yield, a constant, alpha and beta. If we assume the K, alpha, beta all constant, don't worry about it. We just want to know the yield at the lower dose, middle dose, and high dose. What is the relationship between the yield of a chromosome aberrations and the dose? At the lower dose, say 0.1 grade, and the yield would be 0.11. At the 0.2 grade, the yield would be 0.24. So if you compare the yield to the dose, it's almost a linear relationship. Okay? But once you move into the middle dose range, 1 grade, 2 grade, and 3 grade, the yield will be 2, 6, and 12. So as the dose goes up, the yield bends upward very fast. So the ratio of these two doses, 1 and 3, will be factor 3, but the ratio of the chromosome aberration yield will be factor 6. Okay? But most times, if you look at the literature, if you want to check for useful information as a microdosimetry or biodosimetry, you usually look for this range, say somewhere between 0.2 and 1 grade, and they still fall into a more or less like a linear relation area. Okay, but once you get into very high dose, you see that the curve is bending even faster upward. So that's, if you don't remember how this bending relates to a different type of yield, this is a way to memorize it. Now, the different type of aberrations also dictated by the dose rate. We said the two types of aberrations, either the deletion or the exchange. For the deletion, there's really no dose rate effect, because once it got hit, broken, lost, doesn't matter how long or when you measure them, so it's always a linear relationship. But for the two hit aberrations, that's the rearrangement, you do have the time factor there, which the dose effect really plays into it. And in this case, as dose rate decrease, the aberration also decrease. Why? Because you get involved the repels, when the broken joint do not exist there, then you're not going to have the rearrangement, because rearrangement you will need at least 2 broken ends. If the number of broken ends becomes smaller, then the chance of rearrangement also gets smaller. That's why you have this kind of relationship. At the lower dose, now the yield from this rearrangement is much smaller than the rearrangement from the higher dose rate. So just to summarize everything, the chromosome rearrangement can only be observed at the metaphase. That's very important for the laboratory demonstration. That's the only place you can see the chromosome. Or you have to use a special technique called PCC, which we haven't talked about it. We're not going to show you now doing this. This is basically just use the condensation protein from the mitotic cells to force the interface cells to condense your chromosome. But normally we don't do that. And we have the difference between the chromosome aberrations and chromatid aberrations. A lot of time you will ask about this kind of question, so you know how they are different. It's based on when the damage was done. And the yield for deletion type of aberration is represented by the simple linear function. The exchange type of aberrations are much more complicated. They're both dose rate and LET dependent, and the different type of rearrangement, either symmetrical or asymmetrical. The phase of the symmetrical asymmetrical are different. Most times these cells survive. They may get into some of the carcinogenesis, but most of the asymmetrical rearrangement lead to cell death, and that's the equation to describe it. So the next thing is how you're going to prepare your cells to get the chromosome out, and then look this kind of a relationship between different type of radiation, different amount of radiation, what kind of chromosome aberrations. And I'm pretty sure that very few people in this classroom have done the chromosome preparation before. In fact, many of our radiation biologists have never done this kind of thing before, so it's a good chance to at least learn how to do it. Now, the equipment for doing the chromosome aberrations are quite simple. You just need a sterile hood and a good incubator. And the centrifuge could be any kind of centrifuge, but we prefer a microcentrifuge. I'll tell you why later. You definitely need a good microscope, upright microscope for a regular tissue culture work, and a good upright microscope for looking at your slide for a good chromosome, either picture or identification, an inverted microscope for tissue culture. This is a magic equipment, a slide warmer, just hot plate, which you can sort of modify the temperature, and to allow you to get a good chromosome spreading and radiation sources to get to the dose response curve. Supplies, you need some tissue culture flask to grow the cells, definitely come with the tissue culture mediums, a good grade of glass slide. This is an essential chemical. You have to have it in order to induce the cells into mitosis or block the cells at the metaphase so that you can see the chromosome. And you need some of the simple chemicals such as methanol, ethanol, acetic acid to fix the cells so that later on you can spread the cells and release their chromosome on the slide. And you need some salt like the potassium chloride or sodium citrate, and basically you use a hypotonic solution of this salt to sort of swell the cell, make cells fragile, so when you hit the cells to the slide, they can open up and release the chromosome. Now, the procedures of doing the chromosome spreading involve 4 sort of simple steps. The first is cell culture, which is very, very important because most time, if you take the peripheral blood, the lymphocyte as your sample source, those cells normally don't divide, so that the chance of getting any mitotic cells is 0. If you have 0 mitotic cells, how are you going to see the chromosome? And even you work with a very well-defined tissue culture cells, they divide very rapidly. The percentage of mitotic cell normally you can get is about 1% or less. So you have to have a way to force the cells to divide and also have a way to stop the cells at the mitosis so that you can get a good mitotic index so that your recovery of the cells that will show the chromosome to you will be higher. Once you have a good growth condition and allow them to grow into the mitotic stage, you have to harvest the cells. First, you have to block them at the metaphase by using the cosmid. Once I block there, you're going to treat the cells with hypotonic solution that's made by the salt to swell and weaken the cell membrane. And so after that, you have to fix the cells so that they can preserve to be used later. And the fixation is usually done by this magic solution, the 3.1 ratio of methanol acetic acid. So not only to preserve cells, also make the cell membrane very fragile, so they can be broken very easily. The third step is called chromosome spreading, and this is the part that you're going to experience yourself later. We have done the other things for you. We have the cells already in the fixative, but it's you going to do this real chromosome spreading. If you couldn't get a chromosome spread, you're not going to be able to get anything out from it. So basically, it's a drop of cell suspension are placed on a slide and allowed to dry in a controlled fashion. The controlled fashion is very critical. If you don't do it correctly, you're not going to get the chromosome spread on the slide and leading to a chromosome spreading. The last step is once these chromosomes are spread on the slide, you want to age them. Basically, you use dry heat or use ethanol to denature the proteins and remove the waters of fixative and enhance the adherence of the chromosome to the glass slide. And here it's very important. If you don't denature, remove some of these things, your chromosome spreading is not going to be clean. So that you'll see the chromosome, but also you'll see a lot of background from the proteins and other cell debris that you're not able to tell even the chromosome are intact or not. So this is a very critical stage. You want to get a clean preparation. So let's go in step by step of some of the details. And because some of the things you're not going to do yourself, so I have to just describe to you in case that you have to do it all by yourself, and you know some of the points that you have to pay attention of. Let's assume that we're going to take the peripheral blood. This is going to be human peripheral blood. And we take the whole blood and we'll put them in a cultural condition. Most of the time we use 1640 rPMI. It's a magic tissue culture medium. If you do tissue culture work, you know that most of the human cells, whether it's normal or tumor, now this will provide most of the time the best growth condition. Use 10% fetal calf serum. Use a Ph.D. Very, very important. You want to stimulate the lymphocyte to divide. If they don't divide, you're not going to get any mitotic cells or chromosome. For about 72 hours, you add colchicine for 40 minutes. Basically, you block enough the cells into the mitosis so you can collect them. You suspend these cells in 0.075 molar potassium called a hypotonic buffer for about 15 minutes at 37 degrees. All these things are very, very critical. Now, you have to do it right. If you don't, you're not going to get any chromosome spreading. And you'll find out about half hour from now, if you don't get chromosome spreading, you'll be very frustrated because nothing can be done to go on for this line of research. After that, you add the fixatives. That's the magic 3.1 ratio of methanol to acetic acid. And after that, you will do 3 wash. That means you take the cell suspension, spin them down by centrifuge, and remove the solution, then add the fixative, and repeat this 3 times to clean off some of the cell debris or proteins, other things. Then you can store the cell pellet at minus 20 degrees. And this can be stored for a long period of time. And up to a year, and if you really want to be careful on this kind of thing, you have to resuspend this cell pellet into the fixative again before you do the spreading. So you have the cell pellet, and you're ready to do spreading, but I want to say a few words about a hypotonic treatment. And we only give you one condition, that is this one. It works beautifully for lymphocyte, But if you use this solution to work on other cells like the fibroblasts or say some of the human tumor cells, it won't work. You'll get a very lousy result because every cell has its own characteristics in terms of how sturdy they are. The purpose of the hypertonic solutions is that you want to swell the cell to the point it doesn't burst, but it still retains some of the integrity of the cells. So you have to use different kind of hypertonic solutions. So for most other type cells, then you have to use this particular one, the 1:1 ratio of KCl and the sodium citrate at 37 degrees and 12 to 20 minutes. Now, even you use this solution, sometimes still doesn't work well for you. You do the dropping, you don't see any chromosome. What do? You have to come back, look at, did I really make the cells swell enough to get the chromosome? So some of the factors you have to consider is that if you allow the cells in the hypertonic solution too long or too much of the hypertonic strength from the solution, what you'll get is a longer and thicker chromosome, okay? But less refractive sort of in terms of its morphology. So sometimes it's very difficult to see a small breaks for such preparations, so that your estimation will be underestimated the number of breaks or chromosome aberrations. On the hand, if you do it too long, you get into a situation you might see a good preparation. You say, let's shorten the time or the hypertonicity of the solution. What happens is that you get a lot of cell debris around the chromosome. Again, that's a problem because if any particular chromosome exchange because it's masked by the huge amounts of proteins and other things, you're not able to see. So you just have to play around these things well. Now, what is the magic process of dropping the cell to the slide and get a chromosome spreading? If you can have a time-lapse camera hooked into your system and look step by step what's going on. This all happens within about a minute, so it's a time-lapse camera. You have to have those fast speed device so you can see a slow motion of what's going on. First, after you drop the cells to the slide, the cells will touch the glass slide and become immobile because lymphocyte in solution, they move around, and you don't want to have a moving chromosome on your slide. You want the chromosome to be stationary. After a few seconds, 20, 30 seconds, the fixative start to dry. While the fixative is drying, the cells with metaphase chromosomes start to flatten out and spread their content. And that's called the chromosome spreading. Okay? And once the fixative is completely dry, the nucleus cells, because you're not going to have every cell in the metaphase stage, you may still have a lot of cells in other stage of cell cycle, so that they're not going to give their chromosome to you. But what happened to those cells? Their nuclear material is still also going to be flattened out. So that if you look at the slide, you'll see a lot of black circle around. Those are cells which are not in the metaphase, but well, that's the nature of the cell growth condition. Now, so what is the force behind these steps that makes the chromosome spreading? It used to be thought that it's a gravitational force. It depends on how hard you drop the cells to the slide. It used to believe that you have to drop the cell at a certain distance, so the gravity will make the cells hit the slide and splash, and depending on how much splash, you get how much spreading of your chromosome. Too much splash, the chromosome spread everywhere. You don't know whether this chromosome is from this cell or from other cell. Not enough distance, the chromosomes all crumble together. You cannot separate each one of them. But after this, the high-speed camera observation and try different ways, it turned out that has nothing to do with the height or the gravitational force. It's really the second part that makes the chromosome spread out. So the different height only help to distribute the cells more evenly on the slide. So if you want to have an even distribution of your chromosome, and you can experiment out what is the perfect height. Actually, even that is not very important. You can change the concentration of your final solution to make it spread evenly or not. Much of the chromosome takes place at time when the fixative evaporates from the spherical surface of the cell. It's really the evaporation force of the solution that pulls the cells apart. So that's where you have to pay most attention. That is, if you want to do any intervention to make a good or worse chromosome spread, that's the time. If you do everything after that, when the fixative is evaporated, you can never change the outcome of your chromosome spreading. So anything you want to do to improve that has to be done before. So that will involve many factors. The solution you use, because that will determine how much force the solution will apply on the cell, and that also determines how long the evaporation will take place, and this kind of thing. That's why we get into some of the tips and troubleshootings for getting a good chromosome spreading. And because it involves the solutions, so we have the fixative hypertonic buffers, and also involves how you dry your slide. And dry too fast, too slow, you get a different kind of result. Also depends on the humidity of the room. Of course, if you are given a perfect laboratory with a perfect temperature control, but you know that even a brand new building, you might not have that. You might not have a perfect humidity control, because ideally you like to have between 30 and 35% of a relative humidity all the time. You know that's not the case, but that also will affect the outcome of your chromosome spreading. Now, you can use other ratios than the 3.1 ratio simply because methanol and acetic acid evaporate at different rate. Alcohol evaporates much faster than the solution, the acetic acid solution. So if we want to do a fast evaporation, you add more alcohol. If you want to the evaporation go slowly, then you add more acetic acid. That's why you can change this ratio. And also between methanol and ethanol also can change the evaporation rate. The evaporation rate will determine how well your chromosome spreading is going to get. Hypertonic buffers, like we discussed before, will determine whether you have enough of this destructive force to make the chromosome to spread out. And we'll talk more about these two factors. So you will know immediately after you drop your cell to the slide whether it's good spreading or not. If you get a lot of broken chromosomes, you know that you break them too much or too easily. It's either because you have very fragile cell palette. We're going to go back a little bit about how to get a good palette. Or the other way is that since the palette is already in the fixative, you cannot reverse the process. So what can you do to improve from that point on? What you can do is lower the drying temperature a little bit. In that case, that the slide or your sample may be able to absorb or more moisture from the air that will slow down the process a little bit, and that will give you a better spreading. The other case is that immediately after you drop, you'll see that in a few minutes now that you look under the microscope, you don't have a chromosome spread out. They just all stuck together as a one big black ball. So what are you going to do? What you can do is that you can extend the drying period. In this case, if you want to play with the solutions, what you can do can extend the drying period. You can reduce the alcohol content of your fixative. So you can resuspend your cells, pattern into different kind of fixative. Or you can increase the humidity of the room, which you couldn't do that well. So what you can do is that you can put the thing into a humidified box and to do that. Now, we said that we prefer to have a microcentrifuge for this kind of process because the high-speed centrifugation would increase the yield and improve the quality of the chromosome spreading. Because the particular centrifuge we're talking about is the microfuge that uses this particular vial, the 2 ml vial, with a round button. And in this case, you will spin the thing at a higher speed, 6,000 to 7,000 RPM in a shorter period of time. The pallet will be packed better, and you're not going to lose any cells to the cell wall. And You can do these things after the fixed state is added in, because basically you just want to make the palette as compact as possible. You have to have a good grade of a glass slide. Don't go for the cheap slide. So people have tested different brand of slide, and some of the commercial available pre-clean slides are very good. One example is the slide from Ph.D, but has to be gold label slide. They are the most expensive slide, but in order to get a good result, you have to pay the price. If you don't trust even that kind of a commercially available slide, you can do the cleaning yourself by repeated wash of slide in the sequence acetone, HCl, ethanol, then finally with triple distilled water to get a very clean slide. And sometimes even say the commercial or the available pre-clean slide are good, you still make sure there's no dust or cardboard or paper residue on the slide. That can completely destroy your result. Now there are some sort of rule of thumbs if you can follow. That's before you drop the cell pad and after you drop cell pad to get the best result. Normally you do this dropping on the dry slide at room temperature. But if say the humidity of the room is low, what you can do is that you can pre-chill the slide first to about 0 degrees. The purpose of that, the cold slide will capture the moisture better, then that will allow the evaporation go on a little bit slower and give you a better result. But how about the humidity is high? In this case, you can do the opposite way. You can warm the slide to about 37 degrees to improve that. Or if the humidity is really, really high, which may happen in the summertime, you get over 80%, 90% humidity, what you can do, you can soak the slide with a fixative before you drop the thing onto the slide. Other trick is to use some few drops of acetic acid on the slide to improve the chromosome spreading, because in that case you can increase membrane fragility. After you drop, you look the slide, they look good. Now what you should do to keep that good condition. Normally you let dry in the room temperature, or you can use the hot plate, and during rainy days or high humidity to reduce that the drying time a little bit. Or when the humidity is very dry, you can use the hot water vapor, which you add the temperature and the moisture to the surface of the slide. Now these things are very scientific, but they help to make the slide look better. So you're going to try some of these things during the next hour. We're going to do the lab demonstration back to the basement laboratory again, the one that we did our first lab demonstration for the cell survival assay in the basement. The room is 60, 24, and 25. We have 3 sets of things for you to do. One is that you're going to personally doing the chromosome spreading. Although we don't grade you, we can take a look your final product and say you did a good job or not. But at least you get that experience to see if you can get a good chromosome spreading or not. Ying will be the one to show you how to do it. Then she will provide you with prepared sample to do it. Then we also will let you to take a look at some of the chromosome operations with microscope. It's easy to show you on the slide here and point out this is it, this is that. Now it's your turn. We don't tell you that particular chromosome has been radiated or not. So you have to tell us, number one, whether this is radiated chromosome or not. And secondly, you have to tell us how many pieces of operations in that particular chromosome spreading. We also have some of the images that we can show you on a computer screen. The difference between these two is that certainly it will be nice and easy to work at your own time and leisure to look at those images. But sometimes the image is not taken at the perfect condition. For instance, if it's off focus a little bit, then how do you know it's a break, it's a 2 chromosomes stacked on top of each other, or they are the real rearrangement? With a microscope, you can do a small adjustment of the focus and to reveal the difference of the two. But each one has its own advantage, disadvantage, and So I just want you to take a sort of personal experience of these things. So that's what we're going to do the next hour. So hopefully after that, one of these days you can walk into a lab that say, I've done the chromosome aberration before. Okay, any question? If not, we reconvene in about 10-15 minutes down to the basement laboratory area. Okay. And we will divide the group at that time.